for my students, this may help you because this may start to be where you kind of got lost. So, for lesson 1.6, number 59. Express each relation as a table, a graph, and a mapping, then determine the domain and range. To not bore you, I'm only going to do one of these. If you can do one, you can do them all. So, how do I make a table? Bring it up to me, I'll sign it, you can go. Okay? You have a pass?
Yeah.
So after he comes back, I'll sign it.
All right.
Go. Okay? So in these, I can just list them in the table in the order that they're there. -2, 4. -1, 3. 0, 2. -1, 2. And if I'm supposed to be making a table, okay, for the mapping, what do I need to do? I need to list my x values what? What's the key for the mapping? Putting them in what order?
Least to greatest.
Least to greatest. So the smallest number I have there is -2. I have -1 2 times. Then I have 0. And I have to draw the oval around it. For my y values, what's the smallest y value I have? 2. Then 3. Then 4. Now I can map. The first ordered pair is -2, 4. So -2 goes to 4. -1 and 3.
0 and 2.
Thank you.
-1 and 2.
So, by the way, even though we hadn't learned this yet in lesson 1.6, is this a function?
No.
No, why not?
That's 2x.
The x goes with 2 different y's. Awesome.
Or, yeah.
To list my domain and range, you do the brackets, and again, list them from least to greatest. And my range. Okay? Again, from a domain and range, I don't know which x value goes with which y value. I don't know from a domain and range what repeats. I just know the lowest x value I have is -2, and the highest x value I have is 0. Okay? From that, you should be able to do lesson 1.6. Are there questions on lesson 1.6? I feel like the biggest question, the biggest issue we had with the mapping was just it was different, and the idea they have to go from least to greatest, and I want the oval. I got really picky with my class about the oval. Okay, we got it now? Okay. For section 1.7 on functions. So, if you have it in front of you, number 65, is that a function?
Yes.
Why? You're correct. Why is it a function?
I just knew it wasn't because 2x is 1.
So
There's
basically,
not 2 the same.
right. So basically, each x value pairs with its own y value. Okay? Number 66. It's kind of hard to see, and I don't have a graph here, but you have some dots that look like that. Is that a function? It actually is, because if we were to kind of even connect them, it passes the vertical line test. And it's easier to see on your paper. This to the left is actually one space over on the x-axis than this one. So it passes the vertical line test. Let's look at 68, 71, 72, and 73. Okay? For 68, 71, 72, and 73, they gave you two different equations. They're actually functions. Okay? And I feel like actually in my class we did this as a warm-up the other day. And if you're in my 7th period, we actually did this as a warm-up. So for number 68, am I using the f of x equation or the g of x equation? And number 68 says f. So am I using the f of x equation or the g of x equation? The f, which basically means I'm going to take that equation, which was 2x plus 4. And I'm going to substitute the x value, whoops.
Oh, I totally did that wrong.
Okay, well, but now if you know how to do it, then we can fix it. This is basically a different form of writing out substitution.
I put like the equation, like 2x plus 4, and then parentheses.
Okay, so now you know what to do. You're taking out the x value and putting in -3. -6 plus 4. So I could solve that. Correct? Following what I did there? Okay. I'm going to jump ahead for a moment to the 72, because 72 is also an f of x equation. And 72 says put in m plus 2. So that means I'm going to take this equation, and instead of having the x, I'm putting in m plus 2. That looks weird. I get that. We're just working on understanding substitution. I cannot add m plus 2, can I? Why not?
Not like terms.
Perfect, not like terms. So I have to distribute. 2 times m is, and 2 times 2 is, and then I still have this plus 4 over here. And what's 4 plus 4? And that is your final answer. I can't combine anything. Do we get that one? Now I'm going to talk about 75. So 75 says identify the function graphed as linear or nonlinear. Then estimate and interpret the intercepts of the graph, any symmetry, where the function is positive, negative, increasing, and decreasing, the x-coordinate of any relative extrema, and the end behavior of the graph. So this says years since 1980. And this says number of patents in thousands. I don't think you can read my writing, but that says patents in thousands. And the graph looks something like that. So before I even talk about numbers, guys, is this linear or nonlinear? Nonlinear. Okay? And by the way, it's only increasing. Because remember, we read the graph from left to right. So as we go across, all it is doing is increasing. Okay? So, where is it positive? What does positive mean? Does anyone remember? Positive actually, we learned, means technically, in this case, above the x-axis. The whole thing is above the x-axis, right? So it's positive everywhere. They want to know the intercepts. Is this graph ever hitting an x value of 0? No. Which also makes sense in this case. Because, sorry, not an x value. It's never actually even hitting the x-axis. I think I said x value of 0.
It's not going up.
So it's never going to be down here. Hit the x-axis just means, is it ever going to touch this line? No, it's not. You can kind of just see that there. It's going up, which makes sense because we're getting more years since 1980, right? Now, maybe at one point, it never hit this. Now, the patents, if you look at the graph, it's kind of hard to tell. This says 80, and there's like a little squiggly thing, but this is about halfway. So maybe I could estimate 60 for that, which means my y-intercept was at 60, and 60, the y label, is patents in thousands. So how many patents can I estimate were issued here? 60 what? 60,000. So, and this said year since 1980. So what the graph is saying is in 1980, about how many patents did the U.S. issue? 60,000. Do you know what a patent is? Let's start there. Okay, so a patent is basically a way for you to safeguard something you invented or created. So if you invent something new, you apply to the patent office, and that's your protection from anybody else using it. Like Coca-Cola has a patent on the name Coca-Cola. Nobody else can use the name Coca-Cola without their permission. Okay? Technically, right now, you have not patented your name. If I wanted to open a car wash and call it your first and last name, I'm not saying any names here, car wash, nobody can stop me because you have not patented your name. So you all could go out and open up Stephanie Falk's Car Wash and use my name, and there actually would not be anything I could do because I have not patented my name. Now, if you are the Kardashians, they have actually patented their name. You cannot go out and make new lip gloss and call it Chloe K. She's patented her name to make sure that doesn't happen. But that's what a patent is. Okay? So it makes sense that in 1980, there were about 60,000 patents. It's increasing. More people are patenting their names or their designs or their inventions. So like when you create something really cool in your graphic arts class, yes, you, I'm pointing to you, who asks for my paper all the time for graphic arts. If you made some really cool design and you didn't want somebody to be able to copy it, not only do you have to put your name on it, you actually have to patent it.
Yeah.
Okay, so that's what it is.